today I'm gonna talk about like how you can build interactive apps with Rust and WebAssembly. By interactive, I mean with visual and with image. So my name is Poom. Right now I'm starting job next week as software engineer at Metabase. But so far I have been co-founder of Creators Garden. So we are like a group in Thailand who do interactive things. So like for me myself, I have two interests. First interest is my life is about low-level computing. I'm interested in hardware, in reverse engineering and building operating system. But my other interest is art and culture. So let me show you some of my past projects. So I have worked in an embedded system in space before. So this is called the MESSE, the molecular encoded storage for space exploration. It's a DNA storage that can store data in DNA, and we write a hardware to record the experiment in space. Another project I did is with MIT and with a Thai choreographer called Cyber Subin. So you might have seen that a little bit earlier. So in this project, it's an interactive project where it's an AI, where human can dance with AI. So like you might see that a little bit earlier. The audience have the microphone and they can say to the AI, for example, they want to change their energy or they want to change the rotation. And the AI would respond to that dance. So we showed this off in Taipei a little bit earlier. Yeah, so I'm from this group called Creators Garden. So we do a lot of like communities and projects in Thailand. So we talk about biology, we talk about maths in Thailand. Yeah, so the last project we did is actually 2 days ago. So this is called the Algorithm, a bit of Thai tunes. So we have 12 artists in Thailand, 6 of them who create visual, like this you see on the screen, like the visual projected on the building. And 6 of them, they do sound, so they create music with code. So everyone used like slightly different tech stack. So some of them, they use pure data, they connect data together to make music, like operators. And some of them, they write JavaScript or GLSL to make image. Okay, so this is like a thought experiment I had before. What happened if we combine like the rigidity of operating systems, like the way we can express so much with so little, with the art form of art and culture. So what if we can build a tool that would allow us to use very low level components to create art, essentially? So this is like, that was the source idea for my project. So this one is called Visual Assembly Canvas. So essentially it's a tool where you can animation of that apple, and I write assembly to decode that. So you can do that. So I think this project really encompasses 2 things from like the 2 dynamic I told you earlier. There's the computing element, but there's also the interactive, the art, the visual. So today, let's first focus on the computing. The question is, why do we need to build our own operating system, our own compiler? The reason is, do you remember what it was like, let's say 50 years ago? 50 years ago, I imagine like when you were getting a new computer, let's say Amiga, you might get something that's very easy to work with. You can write in a language that's very close to computer. But for today, imagine like what you have to do just to build a web app. You have to know like JavaScript, you have to know React, you have to know Webpack. There's a lot of abstraction. So the idea is, what if you just build your own operating system? Then it's a lot easier, then you have much more control, and it's very portable. I actually got the idea from this game called Shenzhen.io. I'm not sure how to pronounce this, but essentially it's a game where you work as a member in a Chinese factory, and you have to build your own circuit. So you have to connect them together, and you have to write assembly to connect it. So at the start of the game, you have to print out a backup paper that would be like the instruction. So you would have to know, okay, there's an add, there's a sub instruction, right? And then you would write that together and connect it together. Like this is just a game, but people have gone really crazy about it. Like some people, they try to make like a little display. Some people, they try to write Mandelbrot in pure assembly, or some people, they write a maze game. So it's very amazing like what people can do with just assembly. So that's an inspiration for me. Like, so what if you can do that, but like not as a game, but something you would use in real life? What if you can build an OS and an instruction set from scratch? I got an inspiration from this person at the 100 Rabbit Labs. So he built a project called the UXN project. So he said he likes to go on a boat, he likes to go sailing, but on a boat, the internet's very bad, right? You don't have internet. So the programs he used to have were very big and bulky, like Photoshop and Ableton. So he wanted to build his own operating system that would allow him to have very specific, very small stack. So the UXN is actually runtime. So it's like ARM or it's basically like, yeah, x86 assembly or ARM, and Vavara is his operating system, and Tall is his language. So basically by just one or two person, they build their own OS, they build their own image. So this is the entirety of like the system. So imagine how much instruction ARM or even x86 has. There is so much stuff. But in here, you can build the whole system with just 100 lines of code. Yeah, this is literally all you need. And he also have made a little signs. So this is a comic book where you can read from front to back, and you would know how to program in assembly for that system. So it's very cute. I would recommend checking it out. And the thing is, like starting with that assembly, you can build anything, like even with GUI. So their team, they have built a solitaire game, they have built calculators and clocks and complete GUI. But starting with building the instruction set, so you can see this is their own language. And they even build like a music tool where you can control your music instruments. And they can even run it on old hardware, because like if you want to run your web app, imagine like how much computing power that has. You can't just run it on like old machine, right? But if you write your own OS, you can run it wherever you want. You can run it on a toaster, you can run it on an old Game Boy. So that was my goal. I want to build my own OS just for fun and my own language from scratch. And I want it to be able to run on WebAssembly so that everyone can use it. Yeah, so that actually took me about 320 hours just to like completely build this, and it took me around 850 commits. So that took me like about, I think, for 3 months. Yeah. So just a bit of a content warning. So the content here is gonna get very nerdy. So if you don't understand, don't worry, just talk to me later. So let's start with very simple question. What is the easiest computation or easiest calculation you can do? Yeah, 1 + 1, right? Super easy, every kid can do it. So in order to build a computer, you have to start with that. You have to start with 1, so you have 1, and you do 1 + 1, right? So of course, in my program, you can do that very easily. You can just do a push. So this is a stack machine. So you have number 10, you have number 25. 25 times 10 is 230, which is 00FA in hex. Okay, but how the heck do you build this? I think like there's a model of computation called Turing machine, right? The actual Turing machine isn't a machine like this. It's actually a math equation. So the question is, what do you see here? I see tape, right? There's like a very long tape. So that tape represents what we call memory. So in order to build a proper computer, I think Alan Turing or even other computation model tell us that we need 4 things. We need memory, we need register, we need instruction, and we need a way to run that together. Don't worry, I'll go about this one by one. So first, you need memory, right? You need a place to store your data. So how do you make memory? Oh, of course, in Rust, it's very easy. So you just allocate like a big vector. But to make this realistic, if you look at this, you only have limited memory, right? You don't have infinite memory. So I give myself, about 6, so this number of memory size is about 60,000, yeah. And then you have a chunk of memory. But the problem is, what do you do with that? The question is you have to divide the memory into memory space, right? So the first chunk of memory, I might say, okay, I want this to be our instruction, like push or pop or add, and I want this to be the data. I want this to be something else, and I want this to be our stack. So you have to divide up the memory. So in Rust, it's very easy. You can use a constant. Okay, but if you have a big memory, you can't really do anything. So you need a data structure for computation. In this case, I choose a stack. So in computer science, there's pretty much stack machine and register machine. But personally, I like stack machine because it's really easy to implement. So to operate on a stack, you need access to the register because you need a stack pointer. Don't worry, I'll explain what that is. And you need a stack, which is like the stack of data. So what do you need for a stack machine? First, you just need push. You need to put item on top of the stack. Second, you need pop. You need to pop that out. And you need peek to know what is on the top. Push, pop, peek, and you're done. And next, you would need something that's called register. So what the heck is a register? If you have never done like computer science before, here's a quick explainer. So register is basically at your CPU, you need to have a data source to store like the very basic things. So for me, First, I need a program counter, which just counts what line I am. So right now, I'm basically at line 3. But if you count the memory, it's like 1, 2, 3, 4, 5. So you can see the program counter is now at 5. So as you move on, like in assembly, this will count downwards. And then you have the stack pointer, which just keep tracks of like where are you at the stack? Like, are you here, or are you here? So we know like what's the current size of the stack. So if you write that in Rust, again, very easy. It's basically just a number storage, right? Then you need instructions. So what the heck's an instruction? If you have ever decompiled your program, your computer uses a lot of instruction. So ARM is like, I think quite a lot, but I think x86 is like way more. So you would have instruction like this, like for example, move the memory. So in stack machine, good news is you only need a very few. So maybe you just need push, add the data, pop, get the data out, and you would need instruction to do math, right? To add, to multiply, to divide, and you might need instruction to operate on the stack. Yeah, I'm not going to go all over this, but basically this is all I have implemented and it's enough for literally everything. So in Rust, you can use something called like an enum with value. So I would have like an enum value for push, for pop, for load, for store. So you can add any instruction here. Finally, you would need something that's called a fetch, decode, and execute. So to put this simply, before computers were even a thing, before this in Cold War, in wartime, there used to be a room called computing division. So there used to be a room where everyone is not using like mechanical computer, but they have pen and paper, or like a little bit later, they have like more machines, but then people would literally just write on their paper to compute. So similarly, in computer, we must have something that's called a fetch, decode, and execute. So fetch means to get the instruction we want to push. Decode means what that instruction is. We want to know what it means. And execute means to run it. So in this example, our machine is going to have two things, right? We have the memory space and we have the register of the CPU. So it's kind of like, I recommend this video from Tom Scott if you have never heard of this before. So yeah, you have the CPU and you have the RAM. And every time it's like you take like fetch, decode, and execute. And every time it goes and read the instruction and it runs that instruction. So to implement that in Rust, again, pretty easy. So you would write, so you need a fetch first. So fetch is you look into the memory, like what that instruction is. Right now I know, okay, it's a push. I want to do a push. Then I decode that instruction to know like what do I have to do? Like what is that in terms of memory? Like what is that instruction? And then I have execute, which is basically run that instruction. So here's an example of instruction. So for example, what do you do with add? You have two numbers, A and B, and you add them together. Or what do you do with increment? You just get the number and you increment them. So almost every instruction, you can write it as something like this. Okay, and finally you have the tick. So every time the machine process is gonna fetch, decode, and execute the operation. So this is all you really need to make a fully functional like stack machine. You need memory, register, instruction, and a cycle. But okay, what next? So if you have a computer but you can't do anything, it's like too boring, right? You can't really do much. So I took the time to kind of imagine what do I want to do with my computer? So I go to the drawing board a bit and I draw, okay, I want to visualize the memory. I want to see what the memory looks like. I want to make it beautiful so it's easier to look at. And I want the machine to be able to wire to other hardware like MIDI keyboard or make music. So we just daydream a bit. But back to reality. Right now, like what we have built is essentially just a test case. It's like very simple. You have the instruction and you can run it, but you can't really type it. You need to hard code it. So that's why the next step is you need what's called an assembler. So assembler is for, if you don't know, assembler is essentially if you write assembly like in the text format, you need to convert that into the bytecode that the machine understands. So there's a very good book I wrote called Crafting Interpreters. So this is like a very good book that taught you how to build compilers and interpreters. Essentially, if you want to build an assembler, there's 3 steps. First, build a scanner. So a scanner is essentially reading your text file and trying to understand what kind of token it is. For example, in assembler, you might have a label definition. You may have, oh, this is a string definition. So you have to understand like what kind of token it is. Is it a string? Is it a number? What kind of token? And then the scanner would go over each token and try to produce it. So then we have the parser. Oh yeah, sorry, it goes over each character and try to build a token. So the next step is to build a parser. So the parser, what does it do? Very simply, it goes over each token, right? And then it understands what to do with them. In this case, I want to read each token and I want to actually build a set of instructions that my machine can understand. And then finally, we have assembler. So assembler is you already have a sequence of bytecode, but you want to compile it to binary. So in this case, it's very simple. You just read that bytecode and you try to like save it into like a binary format. So you might add a little bit of header and you might segment it a little bit. Yeah, but this is really all you need to make a fully functional assembler. You need to read the text, essentially. You need to understand the format, and you need to turn that text into, well, opcodes. So this is like what the end result looks like. So yeah, so in here I have like a program. So this is a loop in assembly. So I declare like a label here called loop. And then I basically like write some assembly. Yeah, so if you have never done this before, don't worry. It's essentially like if you write a for loop in C, but you can see here at the end result is producing hex 64, which is 100. So now we basically build a fully functional like assembler that can understand this text and run it. Okay, so here's where I want to stop for a bit and like let me tell you where this project took a big turn. So I went to a music festival in Thailand called The Arch. So The Arch is an EDM festival where people do electronic music, right? But I think in the electronic music, a lot of people, they actually write code. So they don't use guitar, they don't use drums, but they actually write code and it actually makes graphic like this. And it's like very cool. So that's like another inspiration from me. I want to actually build a tool that can make music with code. Okay, Here's another inspiration I get. So when I was working on the AI dance project, so this is called Cyber Subin for those of you who come a bit later. So Cyber Subin is a project where we make an AI dance. So we basically get the data from Thai human dancer in Thailand. It's called the Khon dance. And we use the data from the Khon dance to try to understand how to change the dance data. The interesting thing is that when we were building this project, my team member, he used a tool called Max MSP. So it's a tool that looks like this. So you can write like programs and you can connect them together. Or when we were at the Arch, the artists were using a program called Pure Data that can create music. So do you see the difference and similarities? Like both of these, they are very similar. They have nodes and they're wired up together to make programs. So I think this is like very good when you want to do visual computing because you see the result, like this is 3D. And you can use it a lot of ways from doing music festival to doing like AI dance project. Yeah, by the way, this was written in Three.js and TypeScript. Yeah, so if you're interested in AI dance, you can come talk with me. Okay, another inspiration I have is a game. Does anyone know Minecraft? Okay, I think some of you know. Some of you may be too young or too old. So Minecraft is a game where you can place blocks, but Minecraft has a lot of mods. It's game modifications, and there's a mod called TIS 3D. So in this mod, you can write assembly. But in Minecraft, it's very weird. So they would have a spec sheet like this piece of paper, and you can read to understand how to write assembly. And you can write the assembly like move, loop, sub, and jump. And the program would run in Minecraft. So you can use this in Minecraft to build a factory, to automate a lot of things, but just with writing assembly, and you can see the instruction. So that really inspired me to kind of push this project to the next level. So it's not just an assembly or an OS runtime anymore, but I want to make it interactive and I want to make it visual. So how do you do that? First things first, you need a UI, right? You can't really do visual, you can't do 3D, you can't do music with just command line. So first I use React Flow, which is a library in the JavaScript world. So React Flow allows you to make flowcharts, you can connect things together. And then I write some components in React, such as this visualization. So in here, it kind of draws like each row, right? So 1 is the color red, 7 is the color white. And then now, just with this very simple assembly, you can draw any image. So it's like very interesting. Or if you can connect it together, you can create a construct which can send the data together. Like the send instruction would send data from here to here and here to here. So now you can wire up different machines and they can calculate complex things. So in computer science, there's a concept called message passing and actor model. So what is message passing? So look at a program like this or this. So in order to create this very complex, you basically send the message from one instruction to another. For example, first instruction, you might want to say, draw a circle. And then you might want to send a message there that, okay, please add more circle. And then if you add more message, then it's gonna form like a very good program. Same here. So the concept of message passing is that different programs can send message to each other and change the behavior. So the very easy way to program that is what's called actor model. So in actor model, every single program is an actor. So you are an actor, I am an actor, and we can send message to each other. So for example, I may send a message to you like, please stand up, please sit down. Or you can send a message to me, please shut up, it's already overtime. Something like that. So everyone can have their own message and pass it so that we can control the behavior of other systems. So in Rust, you can use this very easy. You just use a vector and store data, store message. Like I have inbox, which is the message from you to me, and an outbox, which is a message from me to you. And then we write a program that basically tries to route the message. Yeah. So Like, look at this. So I have this program, which is an assembly program. And then when I want to send the data from here to here, it basically sends a message from here to here and from here to here. So by sending message, you can chain together like very complex programs. Okay, so I think I'm not sure if we still have time, but we can do a bit of demo. Sorry, do you know how many time left? Okay, 10 minutes, perfect. That's actually more than I thought. Yeah, so, okay, so let's like do a bit of a demo and try to understand like how the heck this even works. Okay, so let me open my notes. Okay, first thing, let's talk about like the actor model. Let's try to understand like what this thing is. So first thing you have to know about actor is first it's all about message. So it's all about like what message do we want to send to other people. So let me open Rust Rover here. Boop. Okay, so as you can see, this is like my Rust code base. And let's open the code called message. Okay. Sorry, one moment. Message. Okay, never mind, it's here. So you can see like each message is a structure. And each structure here, it has an action, which is like what you want to do. And the sender, which is like where should we send this message to. So if you look at the action here, my program has just like a few action. Like each machine, they can send the data from me to you. We can read the data, or we can tell them to reset. So let me actually show you like how that look like in practice. So here, actually, let me just clear everything. And let me start with a very simple program. So I'm gonna create a new machine, right? So here, just to run it to see if it works. And then I'm gonna send a message from this to the other system. So I'm gonna say send 0, 1. So this is like sending the data, sending the message. And then I'm gonna add a pixel block. So this is where you can draw stuff. And I'm gonna send this. Okay, maybe I need to send 2. Okay, not sure if this is working correctly. Let me do this. Whoop. Okay, so here you can see I have 128 and I send it. So there's like 2 data here. So we can actually inspect this to see like how the data is being sent. Yeah, actually I might show you that a little bit later, but let me just show you like how this works. So first we have to understand like what are the blocks. Okay, yeah, I think this is pretty a good start when to understand this. Boop. So you can see like this is a enum called a block data. So every block in the system has its own enum. For example, the machine block is where you can write code. The pixel block is where you can generate pixel art, like the Thai flag you see earlier. And the plot block is where you can plot data. Yeah, so maybe let's look at the plot block. I think that one should work. So first we have the clock block, which generates like a clock signal and a plot block. So if I write this, then look at what happens. So it's gonna send a rising clock signal, and then it dropped a bit. So at every frame there's a data that's being sent. So maybe if we stop for a bit and we try to get like the block state like this. So you can see like this is the internal JSON of the system. Then you can see every block has a structure. So maybe like the clock one is block 3 and that one is block 4. Yeah. Okay, never mind. So because it's being sent very fast, right now like you can see the inbox and the outbox is empty. But if I put it into like a mailbox that is already overflowing, you might get to see it. Okay, so here's how the ticking works. So if you go to like the definition of each block, like I might go to, let's say, a pixel block. You can see this is like what happens at every tick. So at every tick, the blocks try to process the data. For example, I have the pixel block here. Then the pixel block, when it gets a new data, we do a match, and it maybe might push a new data. So it might display some message. Yeah, or it might read a message. So this is like basically the core loop that makes it work. And another important part is the canvas data. So in canvas here, it kind of stores the whole structure of the canvas. So that means like what kind of blocks there are, how is it connected to each other. And then just with that connection, we can write a program that would handle the routing. For example, in this here, we have a function called route messages. So it would try to understand, like, it would try to get the new message that are being generated, and it would try to send that to the correct recipient. Yeah. Okay. I think another part I want to touch on is the WebAssembly part. So let's go to the WebAssembly code base. So in WebAssembly, you can basically like generate or expose a bit of controllers, or you can expose some functions or some methods. So for example, in this case, I have a bunch of methods that I want to expose. So for example, from the JavaScript side, I want to get some method that would allow me to get the canvas state, or I would want some method that would allow me to add a new block. And then from the JavaScript side, I can call that method. Yep. Yeah, so that's like a quick rundown of how that works. Okay, so since we don't have any more time, so my last message is when you're building a side project, it's very recommended to learn in public. That means just write a blog, give a talk, or share it a little bit so that other people can kind of learn from it and give you feedback. So I have been writing a blog like every day that I do this project. So right now it's about 30 blogs. Yeah, so that is very helpful. So I think that is it for my talk. Thank you so much for listening. Bye-bye.